Okay, so this is the kind of outline of my talk here. I'm going to talk a little bit about my sort of day job career arc, but actually Virgil is mostly the stuff that I did on the side. I wrote some papers in grad school about Virgil, and I kind of carried the implementation forward throughout my work, and so it's not stuff that I got paid for, really. So it's kind of the midnight oil language implementation. I wrote some okay papers about them. They're not groundbreaking papers. I wrote a paper that's never been cited before except self-citation. So it's the least cited paper from 2013 PLDI. That's the distinction that I hope to carry into the future. I'm going to talk about systems languages. I like building systems, virtual machines, and what does that mean for a programming language? I did it the hard way. Maybe you guys, if you're interested, don't have to do it the hard way. You can learn some lessons. But I have an application for it. So it's not just doing a language for the sake of a language. I actually want to achieve goals with it. And because of that, I think I came up with some requirements for what a systems language is, what it means. And then I'm going to talk about some science fiction, which is stuff that I want to do with it in the future. All right, so my day job has been all about programming language implementation, but not necessarily with Virgil. So when I was a grad student at Purdue and UCLA, I worked on a few different projects, mostly Java and Java VMs, so this OVM project. Also worked on Maxine VM when I joined Sun Microsystems in 2007, which is now a full 15 years ago. I worked at Google since 2010. And the first 3 years, I worked on a project that was mostly internal, that was some monitoring things. It's not really language implementation stuff. But then I switched in 2013 to working on V8, primarily working on the top tier JIT. So we built a new JIT for V8 called Turbofan, and that led to WebAssembly. And that's kind of what I'm more known for is WebAssembly. In 2020, we had this weird disease going around. I don't know if you remember that. I happened to be at ANU with a couple of people in the back, Tony and Steve. And I was working on Wizard, which is this WebAssembly engine for research that I'm going to talk about a little bit. In 2021, I was a bum. I didn't really do anything. Actually, I wrote a lot of assembly code. I was a consultant. And in 2022, I started at CMU. So that's where I am now. That's where I'm doing research. Okay, so if I look at it in terms of the languages that I was using and interested in the beginning, like before any of this grad student stuff, it was C++ and C. So those were the first languages that I learned. And then immediately when I started working on Java, actually programming in Java, I got interested in the implementation of Java. That was almost 10 years. And then at some point in 2013, I started working on V8. I did not know JavaScript before I worked on V8. I still don't know JavaScript now. I only wrote enough JavaScript to write test cases, primarily test cases for WebAssembly. So I would put 3 years here, but that's like a very light 3 years. You can also see that there's some other Java in there too. Like when I was at ANU, I was interested in working on what happens if we build a JVM on top of WebAssembly. So that was the Java project. I didn't actually publish a paper about that, but maybe one day. And I did actually write some code in Java when I was a consultant. But WebAssembly is kind of like 8 years, I think, that I've worked on WebAssembly now, and I continue to work on that, and I hopefully will in the future. So there's some themes. It's all around kernels, interpreters, systems languages. This has like been my life. So this is like how I view the world, is through the bottom up. So I was originally tinkering with kernels and things like that, then working on JVMs. So OVM I mentioned was a Purdue project. It was a Java virtual machine written in Java. I tinkered a bit with Hotspot during internship at Sun Microsystems. I did an internship at IBM and worked on J9. And then when I worked at Sun, I worked on Maxine. So that's all in the Java era for me. And then the V8 era is basically the JIT and JavaScript, this little tiny pink thing. And then it's all about WebAssembly since then. But really, the secret is that my secret life, my mistress in all of this has been Virgil, which is this language that I've worked on for almost 20 years that I designed. Okay, so this is kind of the history of Virgil. So in the early days, I wrote a few papers about Virgil for embedded systems. So this is like the smallest embedded systems, microcontrollers. These are things with a few kilobytes of memory. You don't have time to, or really the code space to have like a garbage collector and a runtime system. So this is all, like you compile the thing to C, and like the program doesn't allocate any memory. There's a few papers about that. You can go look them up. I got some inspiration for what the rest of Virgil should look like, just kind of carrying that history forward. I wrote the PLDI paper around here, but as you can see, this is like lots of implementation work that I didn't really talk about. So this is stuff that's going on in the background while I was doing these other things that's interesting and hopefully will come out a bit in this talk. All right, so let's talk about language requirements, because I think actually it would be really great if we had some collection of requirements when we design languages, other than just designing languages because it's time for a new language. So what are they going to be? Requirement number one. I don't think that any language that doesn't have an implementation is even worth thinking about. I think you've got to be able to write code in it and run code in it. But I think that every one of these language requirements is going to have an addendum for systems. So the systems language requirement is that this language can run directly on the target machine. And why do I think that? It comes exactly from this experience doing Java and Java VMs. So I didn't work on JIKES, but I know all the people, many of the people who worked on JIKES. Same thing, implement Java in Java, OVM, implement Java in Java, Maxine, implement Java in Java, and these other projects, implement Java in Java. And they all had the same thing that they must do. Java does not have an officially supported native implementation. So they had to build their own. And that's a lot of work. It's a lot of bootstrapping. And before you even get to the fun part of the systems, you have to do like this low-level stuff of writing a new compiler and all of that, which is really fun and it's good work if you can get it. But if you're not a compiler expert, you're not getting anywhere using Java as a systems language. And I do like Java and all, but it's just not a systems language. All systems languages that I know of, they have an official supported native implementation. So that's the key takeaway. So if you're designing a language to be a systems language, you need to think about its native implementation from the beginning. So this is a challenge. This is a laborious process, particularly if you want to compile to an actual machine, because you're going to need to generate machine code, which means that you need to have an assembler. You have to write the back end of a compiler, which means code gen and register allocation, all those things. I really enjoy doing that stuff, but if that is on the critical path to you achieving a goal, then it's going to delay you for some time. So, and beyond that, you have to build a runtime system and a garbage collector if you have a language that has garbage collection, and you have to start building libraries. But the flip side of that is it's liberating and empowering, because you get to define, obviously designing any language, you get to define your own system, syntax and abstractions, but you can choose the implementation. So this goes both ways. You can choose features in your language that are easy to implement in an efficient way and design out things that aren't. And you can also choose new implementation strategies for things that would otherwise be inefficient in another setting. I find it really interesting because you can interact directly with the kernel and CPU. If you've got your own code generator, then you could define how your data structures work, how your calling conventions work, and all of that. If you don't want to reuse any pieces of existing software, it's going to be more work. So some of these things you can maybe choose, like maybe you can use a compiler backend, giving up some of that implementation freedom. So maybe use LVM, for example, or maybe use the backend of some other compiler. But it's all a choice along the spectrum. Okay, so what's the next requirement for any language? This is not just a systems language. I put it this way: a language should offer programmers the ability to build abstractions the way they want and debug their programs in terms of the abstractions they build. So what that means is basically you write code in your language and you debug code in your language, and you don't have to think about the machine underneath, right? So you don't see, this pretty much implies memory safety, right? You don't want to have your language randomly corrupt the stack, and then you have to debug your program and look at stuff at the machine level because your program went out of bounds, right? So it's not written here explicitly, but I think it's definitely an implication that you want memory safety in your language. So what is the systems addendum? It actually doesn't change much. So this is probably maybe not necessarily universally agreed upon, but I think we can achieve this, still keep that memory safety. But the only thing that I added here is that the abstraction should be efficient. So I mean something specific by that, we'll see it in a minute. But things like there shouldn't be implicit allocations on the heap. Okay, so Steve Blackburn sometimes calls this abstraction without guilt. So how does that boil down in Virgil? So I like this picture. I generated it with one of those AI things. It just came out really beautiful. This is not an actual Virgil programmer, by the way, but this is how I imagine them. Okay, so what does the language look like? So for one thing, the very first version of Virgil had embedded systems in mind. And in particular, embedded systems where you cannot allocate memory. There's only dynamically. So there's only 4 kilobytes. So instead, the way it worked is that you could run any code that you want at compile time. And then you would just serialize the heap. The compiler would serialize the heap directly into memory, and you would just run that way. So Virgil, the sort of new version of Virgil, inherited that feature. You can run any code that you want at compile time, and the data structures are just serialized directly into your binary. The compiler will even optimize your code against those data structures. So we'll do heap-specific optimizations. So for example, right here, we have something that allocates hash maps. There is no restriction on the language. It can be, it's string complete, so you could not terminate, and then you don't get actually a program out at the end, and that's fine. So one thing that I inherited from Virgil is that, from Java, is that all objects go on the heap, and they're passed by reference. So there's no such thing as getting an implicit copy of an object. It goes on the heap, and you're always passing a reference to it. So the mutable data is like there's no copying of mutable data. There's none of that is happening. If you do want immutable data, there's a syntax which looks a little bit like Scala. So you can have like the class here point. There's a couple of arguments, and those are basically just like immutable fields that you have to supply to the constructor. And I didn't know Scala when I developed that syntax, but it just so happened that it popped out, and I guess we just agreed on that. And I like it because that means I don't have to explain it to anyone. If you happen to know Scala, then you would know what this syntax means. I mentioned before that a systems language should have efficient abstractions, and I think that implies that you don't want to have any implicit allocation on the heap. So all the allocations are actually explicit, and these are the only 4 constructs that actually allocate any memory on the heap in Virgil. If you allocate an instance of a class, if you allocate a new array, if you instantiate an algebraic data type, which I'll show in a second, or you do a partially applied function. Virgil doesn't have lambdas right now, but it will, and so there will be a 5th one here, which will be that if you allocate a lambda, you'll get an allocation on the heap. But it does kind of have first-class functions. So something that I borrowed from C# is that if you have an object, so down here, this p is a point that we've instantiated. P.distance, that's actually a delegate. So that's a first-class function which remembers the object that it came from. So the object basically serves as the closure. And since that's implemented as a fat pointer, that's a pointer, that's a pair of an object reference and a code pointer. There's no allocation on the heap. So those always just get passed as 2 scalars. So you can do a kind of semi-functional programming without ever allocating anything on the heap. So it's actually kind of nice. It also has tuples. So T here is actually a pair of 2 values. You don't have to memorize any new syntax. You don't have to use a keyword or anything. It's just you put things in parentheses, and that's a tuple. So this is a pair of 2 floating point numbers. And the syntax for types is the same. You can just put types in parentheses, and there you go. They're never boxed, so they're not put on the heap. They will just be flattened in the same way that some functional compilers will do that for tuples. They're always flattened. This happens in the middle of the compiler, and therefore it doesn't ever have to allocate a heap object for it. So they'll just get register allocated like any other scalar values. Okay, what about generics? So Java has generics that only work over reference types. C# has generics that work over almost any type. You can't use void as a type argument. But most functional languages, you can have any type as a type argument. So Virgil is in that category where you can put any type as a type argument for anything that's parameterized over a type, whether that's a class or a function. And in the middle of the compiler, even though this is semantically invisible how it's implemented, it actually does full specialization so that it never needs to box a value. So in Java, you can only be generic over a reference type, and then there's an additional static auto-boxing thing that happens. You don't need to do that in Virgil. So you can have like array copies, sort, and all that stuff that works on primitive arrays. And that happens through the magic of monomorphization. Another thing that I'm slightly proud of that is not the kind of thing that you can write a paper about is that Virgil has nice enums. So an enum is basically a table in Virgil. So it can have fields or arguments in this case. And so, for example, we can declare this enum here is a day, like the days of the week, and it has a name in English, it has a name in German, and then all the values just have to have a string for each of the fields. And so you can write tables of things. It's implemented as just an index into the table, so this will just be like an integer when you pass them around. And so anytime you access the field of an enum, that's really just an array lookup. There's not even a bounds check because you can't statically go out of bounds. It's enumerated. I don't know why anybody else hasn't thought of this. It seemed kind of obvious to me in retrospect. But again, it's not like super innovative that you can write a paper about that. Algebraic data types. So I wrote a paper in PLDI 2013 about Virgil that had 4 main things, and one of them was not algebraic data types. And I argued in that paper that you could emulate algebraic data types. Even though you can, I knew that it's not a good solution, and I knew that I would eventually have algebraic data types in Virgil. So there they are. So you can define a type, and there's various cases, and they can have arguments. So it's very much like any functional language where you can define an algebraic data type, and then you can do pattern matching. And they are true value types. They have no identity. If you instantiate the same algebraic data type constructor twice with the same arguments, they will compare equal. So semantically invisible if they are boxed or not boxed. It turns out to be easiest to implement them with boxing where they do have arguments, so that's the approach my compiler currently takes. But there's no, your program actually can't see that. Okay, and the last thing actually, I think this, from a usability point of view, this is the simplest to understand. Every time you compile your program, you just give all your files to the compiler and it generates a binary. So there's no linking, there's no ABIs, there's no O files, none of that. You just hand all your source files to the compiler and you can optimize binary. There are some optimization switches, but you don't ever really have to mess with them. All the optimizations that the compiler does are semantically invisible, so you don't have to turn off, for example, optimization to debug your program. So theoretically, you can think of like if there was a build system behind this that cached a compiled code, you wouldn't even have to change the interface. Okay, so we're talking about like the systems language requirement of having abstractions that you debug at the level of the abstractions that you wrote. So I think this pretty much implies that you want to have a memory safe language. So Virgil's core language is statically typed for the most part and is also memory safe. There's some dynamic checks, like if you do a cast, or if you were, it checks for null pointer exceptions, and also for array index bounds checks. And if your program has a bug and you go out of bounds, you get a stack trace. I don't even know why this is even controversial in any corner of the world. There are languages that don't give you that. And I found out that after 25 years of trying, I still have bugs in my program, and I love having stack traces. So the Virgil compiler works very hard to always give you the exact same source stack trace if you do have a bug, even in the fully optimized. There's nothing you can turn off to get rid of the stack traces. They're just super valuable. And that also means that there's no other optimizations that you would want to turn off because none of the optimizations change the behavior of your program. Optimization is not observable. I actually think that this is table stakes for languages, but I know that people disagree with me. And in 50 years, when they can't debug their programs anymore, they will see that I'm right. So there's no undefined behavior in Virgil. And so undefined behavior means something specific in C, which is completely insane to me, but there's none of that. Virgil doesn't have any of that. Your program always behaves exactly the same way. That means that you don't have to debug memory corruption issues. It's always at the language level. You don't have to stare at machine code dumps or any of that. I think that we can move into a new era where we debug programs instead of debugging machine code. All right, so requirement number 3. A language should offer sufficient expressivity to implement large, complex software systems succinctly. The systems addendum, their own implementation. Turns out that languages are hard to implement. A good demonstration of a language at least being useful for something is to implement a language, and why not start with yourself? So self-hosting. This can be the hard way, or even harder than building a language implementation is building a language implementation that is completely self-hosted. But it's also wonderful. It's a wondrous process. If you want to do that on a native target, because we're doing a systems language, and one of the requirements has already been that we want to have a native implementation, it means going one step beyond. So building it, potentially have to build a new assembler, like write the bits of all the stupid x86 instructions they ever came up with. I went and did that. Like, I don't know how many weekends I spent on that. And then the compiler, like you may decide, since we're self-hosting, we're going to build a new compiler for it. We're going to build a new backend, all the register allocator stuff. But actually the interesting things, which we'll get into in more detail in a couple slides, is building stuff like the runtime system in the language. So this is actually where it starts to get interesting. The runtime system, the garbage collector, these are things that are really the dark corners of languages. And this is where, like, having some unsafe features that you would maybe resort to if you were implementing your runtime system in C, these is where they come into the picture. So that memory safety stuff that I talked about, almost a lie, not completely a lie, and we're going to see that in a minute in specific detail. But again, this is also liberating and empowering, because you can, for example, define your own calling conventions. There's nothing about calling conventions that is magical. It's completely software defined. So if you want to pass things in registers, you can. If you want to use the stack, you can. You can abuse the registers and the stack pointer however you want, because it's your code generator. One thing that I love doing is messing with the address space. So Virgil has a trick where there's a region of memory which is mapped as read-only but not execute. And all the safety checks jump to that region of memory. And of course, you can't execute that page, so you get a signal. But since it's readable, there's actually metadata there. So when you get a signal, where you jump to actually tells you exactly all the information about the error that you were trying to generate. But since it's a jump that goes nowhere, it's never predicted to go there by the CPU, and it basically costs you nothing in the branch predictor. And you can really only do that if you control the process address space. So there's some bits that you fob in the ELF file to make a section that's not executable. And you can really only do that if you have your own code generator. I don't think you can do that easily from, for example, just C. The other thing is that you can interact with the kernel and the CPU directly. So we'll see this in a minute, but Virgil, you can actually call the operating system kernel directly. You can pass it whatever you want. And so all the possible things that you could do, for example, on the Linux kernel, you can do in Virgil source code. I would say this is also important from an engineering perspective. Like, we need to be able to check that we can start over from scratch periodically, so that we can take all the tools that we've accumulated down there at the bottom, the crusty native tool chains and ABIs and things like that, and see if we can do it over again. So Virgil does it all over again from user space up. Otherwise, we're going to get stuck with some things that we don't like. So the wondrous tricks for Virgil. So my hard constraint was I wanted to do this with no code written in another language. So my compiler generates ELF files directly. I didn't use any utilities. It has its own compiler backend. So the targets that it outputs are all the bytes are output by my compiler itself. So that's ELF, Mako, jar files, which are really just zip files, and WASM files. I mentioned a couple of the address space layout tricks. There are a couple more that I do here that maybe you don't have to go into all the details. But the runtime system. So the runtime system is the thing that generates stack traces, the thing that manages memory, and it has the garbage collector in it. Excuse me, that's all written in Virgil. And this is where it gets interesting in terms of unsafety. So what are the things that you need to step outside of the language's type system? And I confined it all into this one corner called pointer. So pointer is the unsafe type. You only get that if you're targeting a native target. So you can compile Virgil to the JVM, and when you do that, the pointer type does not exist. So all of the stuff that works on the JVM, it doesn't have to use pointer arithmetic. But when you do target a platform like x86 Linux, then you get this pointer type, and you can do these various things. You can do pointer arithmetic, you get a null pointer, so you can subtract two pointers and figure out how far apart they are, and you can actually get a pointer directly into the middle of an array. And that's what you need to implement things like calling the kernel. So there's actually a really interesting and delicate dance of implementing stack traces. So in particular, like the compiler is generating machine code, and the machine code is got various places that have safety checks in it. And when those fail, you want the runtime system to be able to walk the stack and generate a source code trace in terms of like the file, the line, like the line number, and like the method that you're in. So all that is metadata that's output by the compiler in a particular format. There's basically a binary interface between the compiler and the runtime system, where the compiler generates that metadata, and then the runtime system hunts through that metadata when something goes wrong. In particular, there's these two additional intrinsics. You can get the instruction pointer of the method that called you, for example, to start a stack trace from a method, and you can also get the stack pointer of the method that called you. And now you've got two pointers plus the metadata you got from the compiler, and that starts your stack walk. So the runtime system has some kind of kernel knowledge, so to speak, of how the compiler generates code, and the two have to work together in order to implement this low-level thing. Okay, requirement number 4. A systems language must support interaction with low-level software and hardware using their native data formats. So this goes beyond the self-serving parts of the language, which is implementing the runtime system and compiler for itself, and actually doing something useful. And I would say that systems, notice that this is a systems language requirement and not an addendum to some other language requirement. I think this is specific to the domain of systems, is that they deal with native data formats, and they deal with hardware directly. So how does that work in Virgil? Virgil, I mentioned, you can call the kernel directly. So there's an intrinsic. On Linux, it's called linux.syscall, and it's got a type argument here, t. And t can be anything. So there's no restriction on what the t could be. It could be, for example, a tuple type. This thing takes 2 arguments. One is the system call number, and the t is the rest of it. So for example, if you instantiated linux.syscall with a tuple of 3 arguments, that will expand out into a call where there's the system call number plus those 3 arguments, which would be 4. The compiler knows the kernel calling convention, so we'll put those in the right registers or on the stack in the right location, and then it will emit, whether it's int 80 or syscall or whatever it happens to be for that CPU and kernel, it will emit the code directly inline. And so you'll get a call directly into the kernel, and you'll pass the things that you want. If that needs to be pointers to memory, you can use the unsafe things like pointer at contents, which gives you a pointer into a byte array, or so on. The good thing about this is that you don't have to write assembly. So I wanted to not have like the runtime system written all nice in Virgil, and then there's this assembly code that you have to link against. So instead, most of that really doesn't have anything to do with assembly code at all. It's really just this one thing that you need to do, which is called the kernel. And initially, I was like, well, I will enumerate all the system calls in the kernel, and I'll give you a typed interface to every one of them. But then you quickly realize that there's like 380 of these things on Linux. They change all the time. They're different on different CPUs. And if you wanted to update that and stay in track with everything that Linux is doing, you have to update your compiler all the time. So instead, if there's just one, then you know you're done, right? The compiler is done. You can get to any system call. There's no restriction. So handling signals, I mentioned, this is how it happens. You call linux.syscall of sig action or sig control, and you pass it a bunch of data and say, hey, I want to handle sig seg v, and here's my handler. And it goes off and it calls you back. And it usually gives you a huge pile of binary data that you have to know the format of. But when you do figure out the format of that, you're good to go. So the compiler's job is done. Just give me that system call. And for those kernel system calls that require some data structures, like there's typically some C structs, in particular the sig action thing takes a C struct that has, I don't know, maybe 8 or so members in it. I forget exactly what's in there. You put those in a byte array, and then you pass a pointer to it's very untyped here, super unsafe. But you get the ability to basically pass the kernel anything that you want. So I'm working on a way to make that a lot nicer. So defining structs that have a particular layout so that you can get the bytes in exactly the right place that you want without having to do pointer arithmetic, and also being able to deal with this off-heap data in a nicer way. But those aren't done yet, so I had to do it with pointer arithmetic to start. Okay, requirement number 5. I think people would disagree with this. I know people would disagree with this. But I will stake a claim that systems languages must support garbage collection. It doesn't mean that they have to be garbage collected, but there should be some support in that. And I mean something specific about that. So in particular, eventually you're going to use the systems language to implement other languages, particularly garbage collected languages. So what does that support need to be? So you want to be able to find pointers on the stack, in the heap, and all of that. So I think what you want is the compiler to help you out. If you have a systems language that does not have that support, you have to implement it in terms of handles and all of that. So let me talk about how the Virgil garbage collector works, and that you'll see a bit how that fits into what the compiler must do. So all the things that I mentioned that are allocated on the heap, those are garbage collected. And those things, basically, there's no way to manually free them. They must be managed by a garbage collector. And the metadata that you need for a garbage collection has to be, some of it has to be generated by the compiler. In particular, if you want a precise collector that knows where all the references are on the stack, the layout of every stack frame must be described by the compiler, because it's the only entity that knows about it. So the Virgil compiler generates metadata, including stack and object reference maps that go into the binary. And then that format of that metadata is known to the runtime system. And I mentioned this caller SP and caller IP. These are the things that kick off the stack walk for finding those references. And basically, the runtime system decodes this metadata that's come out of the compiler to know where all the references are in the frame. And it's all uses pointers, so it's all unsafe. I know that this is kind of an open research problem to get a fully verified garbage collector. And since even then, I think this would be difficult to make work in a fully typed, statically typed language. So I gave up and cheated with unsafe code. I implemented the simplest possible garbage collection because the simplest possible moving garbage collector, because I wanted to be sure that I got those stack maps right. Because it turns out that that's a very buggy part of most systems, is getting the stack maps right. So I implemented a simple semi-space collector. It's a chaining collector. Every time you collect, you take the whole heap, which is live, and you just copy it over. And then you copy it back, the next garbage collection. And so you must find all the pointers. If you don't find a pointer, you're going to crash because it goes and overwrites the old space with garbage, a particular kind of garbage that makes it easy to debug. But that was how I worked out all the bugs. All the bugs, right? There's maybe a bug or two back there. I think, obviously, more advanced garbage collectors are important for making the system more performant. So in particular, ones that have write barriers or maybe even read barriers and pinning. But since I have limited time on this earth, I figured, and I'm not a garbage collection expert, I figured I'd move on to the things that are interesting. Okay, requirement number 6. A systems language must be used to implement a real high-performance system. This is the proof is in the pudding. If you haven't built anything that is a real high-performance system, you can make claims about the language, but I think they can always be called into a question. So is Virgil a real system? I struggle with this question often. The compiler is definitely a big piece of software. It's about 46,000 lines of code. It's got many targets. It does like the advanced compiler-y things you might expect. But it doesn't do a whole lot of system-y things. Even though it does all this, it could be written in any language, right? There's nothing unsafe about writing a compiler or compiler intermediate representation or writing a code generator. That's not really a systems thing. But the runtime definitely is. So the runtime has to do all the tricks that I mentioned. It has to do the unsafe things to call the kernel. It has to do the unsafe things to walk the stack. For garbage collection, it actually has to copy objects. So that 3,000 lines of code, I focused on making it really simple. So it's unclear whether or not that's a high-performance system. So we're going to see in a minute that I've started to work on something that I think is a better demonstration of that. Most of the code that I wrote is like tests and demos and stuff like that. And they really don't do a lot of like things that you would call system-y things. So I wouldn't say that this necessarily established that Virgil is a systems language just by this stuff. So then I'm thinking about what is actually a good demonstration. I've talked about the requirements of eventually implementing a garbage collected system. And I thought, well, let's get back to actually building a real big boy virtual machine. So what are the requirements of that? So what does a VM do? It has to load code, validate it. It needs to have an IR of the program, so the representation of the code itself, representation of all the data structures and things associated with that code, a runtime system. It needs to have an interpreter, so all the tiers, right? An interpreter, a JIT, and a garbage collector. So this is what Wizard is about. Wizard is a virtual machine for WebAssembly, a new one for research. I hope that it's going to be a context in which I can explore lots of next generation runtime systems ideas. And I think that WebAssembly has got a lot of nice features about it that makes it easier to deal with than, for example, Java bytecode. I could have gone and said, oh, I will now go back in time 20 years and do a Java VM from scratch. But I figured, no, let's look at the future. Let's do WebAssembly again. So it's written in Virgil. So the entire Wizard engine is written in Virgil. There's no code in C. There's no code in C++ or Rust or anything like that. So it's really going to be a demonstration that this is a system language. And it's also hopefully going to be a language that you do research with. So it's going to be flexible and instrumentable. So doing dynamic analysis and things like that. So I mentioned JIKES before. I'm kind of hoping that Wizard is kind of like the JIKES of the WebAssembly world. I already published a paper that I'm going to talk about on Thursday. I'm going to give away some of the magic of that one in this talk, just a little. But I also have already given a talk that ended up on YouTube. So you may have seen that go by. So some of that will be in the talk on Thursday. Wizard implements the entire spec. So it didn't take any shortcuts. All the hard things that you have to do in WebAssembly to actually pass all the tests are there. And since it's designed to be flexible and WebAssembly is actually evolving, it implements some of the new things coming in WebAssembly, like the WebAssembly garbage collection proposal. So maybe it will end up the JIKES RVM of WebAssembly, maybe it won't, we'll see. Okay, so the first thing that you run into implementing a VM and you write an interpreter is we must represent all the values in that language. So if it was Java, it would be all the values that you can have in Java. In WebAssembly, it has to be all the values that you can have in WebAssembly. And these are the values that you can have in WebAssembly. So you can have a reference to an opaque object. Right now, WebAssembly doesn't have garbage collection, but will soon. So these references are only to host objects, so they're opaque. But the garbage collection proposal adds 31-bit integers, so there's a case for that. And then it's got all the primitives that you see there, 32 and 64-bit integers, 32 and 64-bit floating point numbers, and then WebAssembly has a 128-bit vector type. So this is the actual ADT in Wizard that represents those values. So if you look at it, if this were implemented the naive way, this is going to get allocated on the heap. So every one of these is going to become an object. So if you write an interpreter that uses this ADT to represent all your values, is constantly allocating objects. So if you implement 32-bit integer arithmetic, it's loading two things out of the array. Look, oh, it has to dynamically type check because it's effectively dynamically typed at the meta level. And then it adds two numbers together and then allocates another ADT object and then puts it in. So it's super high traffic creator of things on the heap. And pattern matching is going to like hunt through objects in the heap. So it's not going to be super efficient if you write it this way, even though it's very, very nice. And then like the interpreter's value stack and all those things is going to be represented as an array. It's going to be bounds checked. And if you implement an interpreter this way, even though Virgil compiles to nice, efficient machine code, this is slow. Like this is really slow because you spend all of your time doing this overhead. So the baseline here, 1 is the speed of JavaScript core's interpreter for WebAssembly. So this is the interpreter in Wizard, just like written in the nicest style with ADTs. It's like 100 times slower than another interpreter. This is like a fail. This is the kind of thing where you go back to the drawing board and like, this is not working. So there's actually 3 different targets here. Whizzing 32, that's like compiled to 32-bit machine code, 64-bit machine code, and then running on the JVM. So running a WebAssembly interpreter on the JVM, WebAssembly interpreter on the JVM. So it's not super fast. Also notice that the JVM hates my code because it's written in a very functional style with a lot of those delegates. And my compiler does a lot of smart things with those fat pointers, but the JVM doesn't quite figure that out. I took a pot shot at the JVM, I'm sorry, I had to. Okay, so if you're a grad student, don't give up, just write it in assembly. So that's what I did. I looked at all the possible overheads that you get for the interpreter code. Like, you factor out a lot of things, you make things kind of higher order, and like you want the compiler to inline all those things and undo those abstractions for you. There's bounds checks because Virgil is a memory safe language, right? And then of course there's the value representations that you want to change. And I realized that if I want to spend my time teaching the Virgil compiler all those optimizations, it's going to be a while. It's really fun, but like I do not get to the research result that I need to demonstrate here. I need to move on. So I was like, I will just write it in assembly language. And that way I can be sure that I've got it down to the minimum amount of work that this interpreter needs to do. And I was pretty convinced that I could make a fast interpreter, and I needed a vehicle to do that. So I decided I'll write an assembly. And not only that, that gives me the necessity of dealing with dynamically generated assembly code in Virgil. So I have to interface the assembly code that I write for the interpreter to the Virgil runtime system. So the first thing is picking the right value representation, making sure they're unboxed, and then finding all the other overheads in the interpreter. So I mentioned them, like bounds checks, not inlining all the code, all the out-of-line cases. So sometimes you want to inline, sometimes you want to move code out of line because it only happens rarely. So you can kind of do that manually. So value representation. So the possible value representations for WebAssembly values are these things on the left. They could be the I32, I64, as I mentioned, those are integers, F32 and F64. They could also be these large vectors, which are 16 bytes, and they could also be references. And I realized that if you use a value tag, then your interpreter basically has dynamic types. So you catch bugs in your interpreter. That's good from an engineering perspective. Like as soon as you have a bug in your interpreter, like you will catch it because there's dynamic type checks, right? If you have a value tag and you have a value that's 16 bytes, now you have a minimum of 17 bytes. So I pad that out to 32 bytes. So every value is now 32 bytes. They're stored in memory. They're not boxed. So like they're basically written into as slots. And this is how it works. If you separate the value stack in WebAssembly from the execution stack, then it just so happens that you can overlap the frames of one called function to the callee function. It's not really in this diagram, but it works out nicely. So the key thing is that if you use assembly, you can set this up exactly how you want. And so the other state that you need to keep track of, am I over time? No, I got 15 minutes or so. Okay, so the other state that you need to keep track of is here. So if this is the green box here is WebAssembly code, and an interpreter basically keeps pointers into the code. It's going over the original bytes. If you choose assembly language, then you can make sure that you pick registers for those, so those are never spilled onto the stack. So the interpreter is basically always just using its registers to go through the bytes. And then obviously you need to have pointers into the value stack, so keeping track of where all the actual operands and the local variables are of that function. And then the other state that you have is like the instance and like the function and stuff about the memory. So it turns out that WebAssembly is not easy to interpret in place because it's got structure control flow. It doesn't have jumps. So the innovation here, which you can see more about on Thursday, is that there's this side table. The side table keeps track of the information that you need when you do a jump. Where is it going? Since that's not in the original bytecode, we can put it in the side table, and the side table happens to be always pointed to by a register, so whenever you have a control flow instruction, you can just go where you need to go. So the other thing is assembly. There's no need for bounds checks. Since the code is actually verified by the WebAssembly type system, it's not possible to go beyond the end of the code. If you do go beyond the end of the code, that's a legal implicit return, so that will be checked for anyway by hitting this end bytecode. The side table is the same, right? The invariants that you need to prove that these things are never going to go out of bounds, those are at a level beyond the programming language. So it would never be possible to prove with Virgil's type system that you don't need bounds checks here, but you don't because that's a WebAssembly property. unbox values I mentioned, but also you want to be graceful if you overflow the operand stack. So if the program has unbounded recursion or just uses too much stack, you want to actually trap that. So you don't want to do that with a bounds check. Instead, that's done with a guard page. All right, so requirement number 7, interacting with dynamically generated code from the program. So a systems language must interact with dynamically generated code from the program. Notice I didn't say assembly here. It's almost implied, but not quite. If you had a language that had eval, like JavaScript or Ruby or Python, you can actually do dynamically generated code. You could think of having a JIT at that level that generates more source code. I thought about doing this. Well, maybe Virgil, since its compiler is written in Virgil, it'd be easy to include in your Virgil program, except that you have to generate code really for the target machine. So every construct that you would want would have to have something in the source code. Not only that, you actually are running with the source compiler. And maybe that's like, it's not too big, it's like a megabyte, but maybe you don't need a full megabyte to generate a little bit of code. So what this really means is that you should be able to interact with assembly code. So the fast interpreter that I wrote basically imposed these requirements on Virgil. So it's basically new machine code. So instead of writing it in like a textual assembly language, I wrote it using basically a macro assembler, which is an object that generates machine code for you. So technically speaking, you could generate this code offline, but it was easier to just do it online. So basically the interpreter is just some machine code that's built at like one of the first things that happens when you run the wizard engine. So it actually didn't require any changes from the Virgil compiler to get the code into the system, right? You can do linux.syscall sysmmap, and you can make a new code region. You can give it any permissions that you want, and you can write any bytes that you want in there, right? So that's covered from a language perspective. But to be able to call that code, you need some kind of mechanism to get that into the language, right? To make a function that you can call from the language. And these two mechanisms, forge closure and unpack closure, are exactly that. Forge closure allows you to take an object and a code pointer and turn that into a Virgil level function. So it makes that fat pointer. And so that will become typed at the Virgil level, and now you can call it. And so that code has to be compliant with the sort of calling convention of Virgil. But since I use a fairly standard calling convention, that's kind of okay. And you need the reverse if you want to call code in Virgil from the machine code. You need unpack closure, so you can take a closure from the Virgil world, and you can get the code pointer out of it. So you know the address of the function that you want to call from your machine code. So you have to follow the calling convention and the ABI of Virgil. So there's some kernel knowledge there. You need to be able to potentially access some data structures. So the runtime system in Wizard, it's all written in Virgil. So like the representation of the WebAssembly program is all in Virgil objects. So various things that the WebAssembly code will do need to actually touch those data structures. So knowing how they're represented is done through getting pointers into the middle of an object and computing offsets. So you can generate machine code that potentially reads them. Another dark detail is that WebAssembly has safety checks. So you want to implement safety checks for this guest language, and you need to be able to handle the implications of your guest program violating its safety checks. So in particular, if the WebAssembly program goes out of bounds of its own memory, that's going to create a signal. So you need to be able to handle signals that are not my Virgil program is broken, but it's the guest program that's broken. So the runtime system has the ability for you to basically handle signals within a specific code region that you've defined. So in Wizard, that's like if a signal happens in the interpreter code, then the runtime system of Wizard is going to get the first chance at handling those signals. There's a couple more details here, like that value stack. If you remember, we had a tagged value stacks where one of the values could be a reference. So finding that actual pointer, you need to actually tell the Virgil GC about that. So there's a callback in the GC to be able to do that. And then actually mapping memory, that's typically, the management of that memory is typically tied to an actual object. So there's a finalizer that gets called back when an object dies. So you can deallocate memory that might be associated with that object. So all that basically summarizes to this. So I wanted this research result, which was, can I write a fast interpreter for WebAssembly? And this is how it breaks down in comparison to other execution tiers for WebAssembly. So the red things are optimizing compiler tiers. The blue things are baseline compiler tiers. Those are like single pass compilers for WebAssembly. The orange things, those are interpreters that rewrite WebAssembly code. And then the green thing is my interpreter, which interprets the original bytes of WebAssembly. The axes here are how much upfront processing cost you do on WebAssembly code. So it's a log axis. So the further right you go, the more time that you're spending on processing the WebAssembly code. So this is more in the area of what I'm going to talk about on Thursday with the OOPSLO paper. But this is really just the proof that I can actually achieve something with Virgil other than Virgil itself. There's more to come, more challenges. I'll speed up a little bit. I only have a few minutes left. Now we've got another problem. WebAssembly is coming with a GC extension, which means that the guest language that we implement in Virgil has new types of objects that the Virgil garbage collector has never seen before. Since this is code that's loaded by this WebAssembly engine, it means that there's new shapes. So obviously, you can emulate any object system by allocating arrays of values and using ADTs, but this is super inefficient. So instead, you actually want to define new object shapes at runtime. You want to define an object layout where it's efficiently packing all the fields of the user level objects. And since this is defined by user code, this is effectively it's not possible for the Virgil compiler to see these things. They're really defined by this guest VM. So it requires a new kind of extensibility to the garbage collector in the runtime system. And this is the science fiction part of it. I haven't implemented this. I've only kind of sketched this out in my head. But the idea is that you allow the runtime system to allow you to register new object shapes. So the object shapes are basically, this object is this big, and I have references at this offset and that offset and then the other offset. And the reason why you want to make that as a registration is that you want the garbage collector of Virgil to be able to walk those objects for you. So by having basically a check-in, you're effectively giving the existing garbage collector a new type of shape that it will be able to handle, instead of writing the logic for scanning the object yourself. And in return, the runtime is going to give you the actual header that you need to put on the object in memory, so that whenever the runtime system finds an object pointer, if it finds that header, it knows how to walk that object. There's a few other things that are also ugly details here. The guest language, go ahead.
Okay, you said the shape of the object, but I think you meant to say that per class or per type.
Yes, where the number of types is determined. Yeah, the number of types is determined by the guest program, yeah. So there's a few other ugly little details here too. So the guest language, effectively, you want it, for high performance, you want to do inline allocation, meaning the sequence of operations you need to do to get a chunk of memory in order to fill out your object. That may be, for example, a bump pointer allocation, or it may be a free list allocation. You need to know that sequence so you can generate the machine code for it. So you can't really make that super modular. Similar for write barriers or read barriers if you have them. The inline sequence for that is easy to make that into a function call, but that's typically too slow for a high performance system. So somehow you need a scheme by which you can tell the guest VM what the write barrier is supposed to look like. And these new objects, they have to fit into the existing type system. So you can imagine, like, somewhere in Wizard, there is a class, WASM object, and all WASM objects are going to be effectively subclasses of this object. And that needs to be spelled out so that the compiler can make space for it in its own type testing. So if you ask an object, are you a WASM object, and it's one of these dynamically generated things, it needs to be able to say yes. So the exact layout of those things has to be something that everybody agrees on. Okay. That is basically the requirement number 8. A systems language must interact with dynamically generated data types from the program. This is these new object shapes. All right, so this is almost the last slide. The summary of the systems language requirements. I think the system languages have additional things that many normal general purpose languages do not have, and they are these. It must run directly on the target machine. Obviously, you're not getting anywhere if you have it running on a virtual machine because you have to implement that virtual machine. You should have nice abstractions. You can have nice abstractions as long as they're efficient. You need to be able to build large systems. So if you're continuing building small systems, you're not really exposed to all the challenges of building a large system. You need to be able to interface with low-level code in the hardware. This is something that you don't typically do with the general purpose language where you can get away with doing that through libraries. A systems language has to do that as its bread and butter. Again, the controversial one I think is supporting garbage collection. Supporting it, maybe not requiring it. So supporting it in the sense that the compiler gives you stack maps. That's super useful so you don't have to build a handle system. Proof is in the pudding. You have to implement a real system. I think VMs are really fun and interesting. It doesn't have to necessarily be a VM that you're writing all day, but eventually you have to implement a real system to prove that the language is actually a systems language that works. And if you are building a VM, then you're going to have these two additional requirements, which is adding new target code and new object shapes at runtime. And then there's this other thing about concurrency that I haven't solved yet. This last requirement that I didn't get a chance to talk about. Okay, that's my last slide.
Who wants to ask the first question?
Thank you for the nice talk. So with the recursion that you implemented, with the polymorphism that you implemented, I assume you don't support polymorphic recursion,
Correct.
right?
Yep.
Okay, that's my first question. But the main question I had was with you said that you've got to support stack traces, and you've astounded that several languages don't really give you accurate stack traces. Do you do tail call optimization?
No, I don't.
Could you comment on that decision? Was that a design decision, or was that just a consequence of your implementation so far? Do you intend to support it in the future?
I definitely see the value of having tail calls, and I think if you have tail calls, it's okay to leave out those in the stack trace. I mean, you can't recover them otherwise. I know other systems have a mode where you can go into where you can get the whole stack trace, for example. That may be useful. I can see like having a syntactic hint. So I don't think it should be implicit. I don't think you should have implicit tail call optimization. So if there was like a keyword or something to indicate tail call, I think that would be okay.
Right. Thank you.
Next question.
I noticed you had a special primitive for calling system call.
Yeah.
Why did you do that instead of like a general FFI to call arbitrary code?
Yeah, I think the general FFI thing is actually, mostly I didn't want to implement a linker. So general FFI, where you could have a .o file that links code from another language. Not having that meant that I was forced to do everything in my language. So that is almost like a forcing function for me to be able to do it this way. Nowadays, some people keep asking about that. Like, why can't I get a Virgil DLL and link it into my C code, or vice versa? And so maybe it will be possible to be able to do that. You can generate WebAssembly code that has imports of foreign functions and stuff like that, but that's not quite the same thing. I can see that coming.
Thanks for the talk. I was wondering how you implement like exceptions or like non-local control flow. Like, do you have support for things like set jump, long jump equivalents, or that you find unnecessary? What's your take on this?
There isn't support for set jump or long jump. As far as exceptions in the Virgil language, I'm kind of torn. It hasn't worked out great and it hasn't worked out perfectly in any language that I'm aware of to have exceptions for things that are non-exceptional. So I steer clear of exceptions when I write code. I think somehow you want to encode that in return values, and so ADTs are kind of that in that area. You want to encode like error cases in one of the cases of your ADT. That said, though, if you're implementing a language that has exceptions, it may be nice to have non-local returns in Virgil to be able to do that. So WebAssembly has traps, so the stack can unwind. WebAssembly also has exception handling coming too, and that's done with basically the code that's generated has like checks for it. So it doesn't do direct stack unwinding. It's unclear to me how pervasive like CFI and hardware is going to become. So I don't know if you're familiar with Intel CET, but it's basically hardware checking for CFI where you can't do those old style unwind the stack yourself. So it's unclear to me whether you necessarily need to have that or whether you want your compiler to generate like code that unwinds the stack kind of manually as you unwind. But I definitely don't think that that Virgil should use exceptions in sort of normal programming style.
Ben, thanks for a very nice talk. And really, you had a very pragmatic perspective, I think, in kind of motivating all these design decisions. But I wonder whether what you've come up with might be interesting in terms of formal methods. Could you imagine putting this stuff into a theorem prover, say, and finding interesting properties of your programs? I think it would admit formal methods because of the design decisions you've made.
Yeah, so one thing that's good about Virgil, I think, is the core language is completely deterministic. So it's memory safe and like your programs does not depend on hardware, right? So that's already a good start for any kind of formal method. I would say there's probably a bit of a challenge in formalizing Virgil in that the way conversions work and the way the primitives, I didn't really talk about that, but like I spent a lot of time working out how fixed size integers and floating point and all those things relate to each other and how the compiler resolves implicit conversions. I don't think that's been particularly formalized well for any language that I know of. And that would be an interesting direction there to think about that. But I think the solutions I came up with there are also very pragmatic too. So anyone who wants to volunteer their grad students to formalize Virgil, go ahead.
Do we have a last question while Raphael set up?
So you said you don't have a linker. So do you have support for libraries? How does it work? Do you put the source code and you compile everything? Or do you have a package manager?
There isn't currently a package manager. It's a whole program compiler. So you just like give your source code and all the library source code to the compiler at once, and it generates a binary. It does like a lot of dead code elimination, so you don't end up with the entire library in your code. But I haven't thought about how to make that incremental build yet.
So what are the compile times in the case where?
So the compiler will compile itself in about 0.3 seconds. It's about 100,000 lines of code a second.
Thank you.
All right. Let's thank Ben again.